This is basically the same problem we previously had with one subtle change. We've changed the polarity of the plates from being negative to positive. So if you recall from the previous question, our proton was accelerated and sped up as it traveled between A and B and C and ultimately smashed into the far plate on the right. But if the plate's polarity have been reversed, and this first one now is positive 15,000 volts, and positive 30,000 volts, and positive 40,000 volts, it stands to reason that our positive charge will slow down once it enters that region where there's an electric field that opposes its motion. So it's going to slow down in region A, slow down in region B, and slow down in region C. And our goal is to figure out where will it eventually stop, or will it at all? In other words, we're trying to figure out how much voltage is required to stop this proton. If it's more than 40,000 volts, then the proton will strike that final plate. It'll be slowed somewhat, but it'll still make it to the final plate. If it's less than 40,000 volts, it'll either be in region A, or region B, or it'll be found in region C. So for example, if our stopping potential is between 30 and 40,000 volts, let's say it's 35,000 volts, the proton will slow down, slow down, slow down until it finally comes to rest in region C, where it will no longer have kinetic energy for that split second while it stopped, but all of its initial kinetic energy will be converted into potential. So in a lot of respects, this question is mathematically a lot easier than our previous one. We simply want to calculate its original kinetic energy and see how much potential is required to get rid of all that original kinetic energy. In other words, we want the initial kinetic energy to all be converted into potential. So let's see what that looks like mathematically. So using our principles of work energy, we start with kinetic energy and we want to convert it all to potential energy. So kinetic energy, as usual, is 1/2 mv squared. Mass of the proton is 1.67 times 10 to the negative 27 kilograms, and the speed is 2 times 10 to the 6 meters per second, and we have to square all that. The charge that is moving between these plates is the charge of the proton, which is the elementary charge, as we saw before, 1.6 times 10 to the negative 19 coulombs. And what must be the potential difference required to stop that charge? So when we take this equation and we solve it, we end up getting delta V is 20,875 volts, or about 21,000 volts, which would place the particle between our 15,000 volt plate and our 30,000 volt plate, somewhere in here.